Dear students, welcome to Commissionerate of Collegiate Education Learning Management System. In this video presentation, I am going to discuss about the topic Joule-Thomson effect. Myself, Vinny Teja, lecturer in chemistry, SKR and SKR, Government Degree College for Women, Kadapa. At the end of this presentation, you will be able to understand what is Joule-Thomson effect and what is Joule-Thomson experiment and Joule-Thomson coefficient and also the inversion temperature. Let us discuss these topics one after the other in detail. In thermodynamics, the Joule-Thomson effect describes the temperature change of a real gas or liquid when it is forced through a valve or porous plug while keeping it insulated so that no heat is exchanged with the environment. This process is known as throttling process or Joule-Thomson process. The phenomenon of change of temperature produced when a gas is made to expand adiabatically from a region of high pressure to a region of extremely low pressure is known as the Joule-Thomson effect. Joule-Thomson effect is also called adiabatic expansion of gases. Joule and Thomson observed that when a gas at high pressure is allowed to expand to low pressure region, the gas gets cold. That means, if a gas is compressed to about 200 atmospheres pressure and then allowed to expand through an orifice into a container that is at low pressure, the gas expands and gets cooled. The reason for this is that at high pressure, the intermolecular distances are very less that the molecules experiences the phases of attraction. And when the gas expands, the intermolecular distances must increase, for which the molecules must do some work, or they must lose some kinetic energy to overcome the intermolecular attractions. Since kinetic energy of a gas is directly proportional to its absolute temperature, on an adiabatic expansion, if gas loses some kinetic energy, its temperature is also gets lowered. Hence, by losing kinetic energy, the gas gets cold, and this phenomenon is called Joule-Thomson effect. The expression for this effect is as shown in the figure, where P1 and T1 are the initial pressure and temperature, and P2 and T2 are the pressure and temperature after expansion of real gas or liquid. From this, we understand that more the difference between P1 and P2, more would be the difference between T1 and T2. Now, let us understand the experiment that is conducted by the scientists Joule and Thomson under adiabatic conditions for the expansion of real gases. Now, let us understand the Joule-Thomson effect from the Joule-Thomson experiment in detail. The apparatus used by the Joule and Thomson to measure the temperature change on an expansion of a given volume of gas under adiabatic condition is illustrated schematically in the figure as shown in the below. This apparatus consists of an insulated chamber which is fitted with a porous plug Q in the middle and two pistons A and B on the sides. This insulated chamber ensures the adiabatic condition so that no heat enters or leaves the system. Pressure of the left side of the plug is P1 and that of the right side is P2, where P1 is greater than P2. The gas of volume V1 at high pressure P1 is allowed to go into the part of low pressure through porous plug Q by moving the piston A inwards and is allowed to expand to volume V2 at a lower pressure P2. This process is carried out slowly so as not to change the pressure P1. The change in temperature is found by taking readings on the two thermometers, which are not shown in this figure. And when the experiment is done at room temperature, all gases show a decrease in temperature on expansion, except hydrogen and helium gases. Since the process is carried under adiabatic condition, then Q becomes 0. According to first law of thermodynamics, change in internal energy is equal to heat absorbed by the system minus work done by the system. Since the process is carried under adiabatic condition, Q becomes 0, then change in internal energy is equal to negative work, or W is equal to minus delta E. Thus, the work done during the expansion of the gases under adiabatic condition is at the expense of internal energy delta E. In other words, when the work of expansion is done under adiabatic conditions, the internal energy decreases and hence the temperature of the gas decreases. Since internal energy is directly proportional to the absolute temperature of the system. Joule and Thomson introduced the term Joule-Thomson coefficient. It is represented by μJt for expressing the change in temperature produced by the change in pressure during adiabatic expansion of a real gas. They defined μJt by the expression μJt is equal to dou T by dou P at constant enthalpy. From their experiments, Joule and Thomson concluded that if Joule-Thomson coefficient is positive, then the gas cools on adiabatic expansion. If Joule-Thomson coefficient is negative, the gas warms up on adiabatic expansion at room temperature. And if the coefficient is equal to 0, then the gas neither cools nor warms up on adiabatic expansion. Now let us understand what is inversion temperature based on Joule-Thomson coefficient. At a particular pressure, every gas has a definite temperature at which Joule-Thomson coefficient becomes 0. This temperature is called inversion temperature, which is denoted by Ti. Below this inversion temperature, μJt is positive, that is, gas undergoes cooling on adiabatic expansion. And above the inversion temperature, Joule-Thomson coefficient is negative, that is, the gas undergoes heating on adiabatic expansion. This inverse temperature is written as 2A by RB, where A and B are the van der Waals constants. Joule-Thomson effect is applied in the Linde technique as a standard process in the petrochemical industry, where the cooling effect is used to liquefy gases. Linde used Joule-Thomson effect principle to liquefy air. The air is separated from dust particles and carbon dioxide and then sent into a compressor that compresses it to about 200 atmospheres pressure. The heat produced in this process is removed by passing the compressed gas into the cooler B, in which water is circulated. From the cooler, the air is sent into spiral tube of hundreds of meters length and finally enters into the space of low pressure through the valve. In this process, the air gets cooled by Joule-Thomson effect. This cooled air then enters the chamber E. This would cool the air that enters inside before expansion. From the chamber E, the air again enters into the compressor and gets compressed again. This process is repeated several times in a cyclic process until the air gets cooled below its critical temperature minus 140 degrees centigrade. When the air is below its critical temperature on further expansion, it gets liquefied and reaches the vase flask. This is how the air gets liquefied by the process called Linde's liquefaction. Let us summarize the points that we have discussed so far. We discussed that the phenomenon of change of temperature produced when the gas is made to expand from a region of high pressure to a region of extremely low pressure is known as Joule-Thomson effect. Since the process is carried under adiabatic condition, the work done during expansion of gases under adiabatic condition is at the expense of internal energy, and hence the temperature of the gas also decreases since the change in internal energy is directly proportional to the temperature of the system. Joule and Thomson introduced the term Joule-Thomson coefficient represented by μJT for expressing the change in temperature produced by the change in pressure during adiabatic expansion of gases. If Joule-Thomson coefficient is positive, the gas cools on adiabatic expansion. If Joule-Thomson coefficient is negative, the gas warms up on adiabatic expansion. If Joule-Thomson coefficient is 0, the gas neither cools nor warms up on adiabatic expansion. We discussed that at a particular pressure, every gas has a definite temperature at which Joule-Thomson coefficient becomes 0. This temperature is known as inversion temperature of that particular gas. Below the inversion temperature, the Joule-Thomson coefficient is positive. That is, the gas undergoes cooling on adiabatic expansion. And above the inversion temperature, the Joule-Thomson coefficient is negative. That means gas undergoes heating on adiabatic expansion. We have also discussed about the application of Joule-Thomson effect, that is Linde's technique, where the cooling effect is used to liquefy the gases. I hope you have understood this topic, Joule-Thomson effect, that we have discussed so far. Thank you.